How is it possible for a system governed by precise mathematical equations to become completely unpredictable just because you changed a number by 1/10,000th? For centuries, classical physics operated on a simple assumption: small causes produce small effects. If you add a tiny weight to a scale, it tips proportionally. Everything scales linearly. In the mid-20th century, meteorologists applied that exact same linear logic to the atmosphere. Looking at boards of static data points, the dominant belief was that weather was just a massive math problem. The assumption was that if we simply built better thermometers and more precise barometers, our long-term forecasts would eventually become flawless. Both scientists and the public treated the atmosphere like a giant clockwork machine. They believed we just needed slightly better rulers to measure the gears, and weather would be a completely solved equation. But that foundation overlooked a mathematical property of atmospheric fluid dynamics that would eventually dismantle the era's linear models. In the early 1960s, a mathematician and meteorologist at MIT named Edward Lorenz was testing simplified weather models using early computer systems. He programmed a set of differential equations to track temperature, pressure, and airflow in a closed system, initializing his virtual weather with a starting temperature of exactly 20.000 degrees Celsius. This graph illustrates his first run, which produced a clean, highly stable, and endlessly repeating weather pattern across his simulated days. Then, Lorenz ran the exact same model again, but he altered that initial temperature by an infinitesimally small fraction. He changed it to 20.001 degrees. For 30 simulated days, the two systems matched perfectly. But then, the new trajectory violently broke away. By day 60, it had morphed into a completely different storm system, with pressure differences exceeding 12 hectopascals. A hectopascal is a metric unit used by meteorologists to measure atmospheric pressure, where a 12-unit variance signifies the difference between a calm day and a major storm. Lorenz had programmed identical physical laws and used virtually identical starting conditions, yet the machine produced radically different realities. At first, Lorenz assumed his primitive computer had simply made a calculation error. Scientific consensus dictated that such a tiny input variance couldn't possibly derail an entire system. To test this, he designed a highly controlled second experiment. He froze all metrics except for humidity, which he truncated from a highly precise 6 decimal figure down to just 3 decimals. To rule out a hardware glitch entirely, Lorenz bypassed the machine and manually recalculated key iterative steps by hand. The divergence persisted even on paper. After just 100 hand-calculated cycles, the two storm intensity predictions differed by 40%. The result proved that unpredictability was not a bug in the hardware, but an intrinsic feature of the mathematical laws governing the atmosphere. Lorenz then set up a third simulation, designed specifically to isolate exactly how and when this mathematical amplification occurs. He initialized two nearly identical atmospheric states, separated by a minuscule 0.0001 difference in initial wind speed. After 50 simulated days, one trajectory generated a violent cyclone, while the other resulted in complete atmospheric stability. This graph plots the predictive error over time. Forecasters expected that linear dashed line, a slow, manageable drift. Instead, the solid line shows an exponential separation, with the error doubling roughly every 1.8 simulated days. Lorenz mapped this exponential growth and discovered that his atmospheric equations lived within a specific geometric space, a structure now known as a strange attractor. The strange attractor reveals a strict rule. The system is completely bounded, meaning the weather will never become infinitely hot or cold, but the exact path of the trajectory never repeats itself. Lorenz had demonstrated that long-term prediction collapses not because the universe is random, but because it is exponentially sensitive to its initial conditions. This shift in understanding, where deterministic laws produce behavior indistinguishable from randomness, would form the basis of chaos theory. Lorenz's discovery forced meteorology to abandon the pursuit of a single perfect future. To account for this exponential sensitivity, modern meteorologists rely on a method called ensemble forecasting. Instead of running one simulation, a supercomputer runs a single forecast thousands of times simultaneously, intentionally injecting microscopic variations into the starting numbers of each run. We see the stakes of this math most clearly in modern hurricane tracking. In modern models used by the National Oceanic and Atmospheric Administration, altering a starting temperature field by a microscopic 0.01% can displace a storm's predicted location by over 200 kilometers after 10 days. This map visualizes that outcome. By plotting the spread of these overlapping tracks, forecasters map a probability distribution, which you likely recognize on the news as the cone of uncertainty. Nature remains deterministic, governed by precise rules. But because of this predictability horizon, science no longer calculates absolute certainty. Instead, it maps the boundaries of chaos.